7 mysteries wrapped around a single interstellar visitor. C/2025 I-3 Atlas tore through deep space at 130,000 miles per hour, and what unfolded next left NASA scientists stunned. No visible tail. Outgassing that defied physics. Record-breaking polarization measurements. A trajectory that swept past Mars and Jupiter with unsettling precision, all shrouded in unexplained silence. If even 2 of these anomalies withstand scrutiny, we may be witnessing a comet that no one on Earth knows how to explain. Everything we thought we understood could shatter in the next 5 minutes. So why does C/2025 I-3 Atlas look more terrifying than anyone anticipated? On July 1st, 2025, the Atlas Survey telescope in Chile triggered an alert that would captivate the astronomical community. A new object streaked across the sky at extraordinary velocity, designated C/2025 I-3 Atlas. It stood apart from anything cataloged before. Its hyperbolic trajectory confirmed what scientists had suspected. This was an interstellar visitor, only the 3rd ever verified in human history. Early velocity measurements clocked the object between 37 and 42 kilometers per second, fast enough to escape the sun's gravitational embrace forever. Once it departed our solar system, it would never return. Initial size estimates varied dramatically. Hubble Space Telescope imaging established an upper limit of approximately 5.6 kilometers across for the nucleus, while ground-based observations suggested it could be as compact as 320 meters. The nucleus itself appeared elongated rather than spherical, with some images revealing a stretched, possibly tumbling core that rotated as it traveled. C/2025 I-3 Atlas posed no threat to Earth. Its closest approach would keep it 1.8 astronomical units away, over 270 million kilometers, safely beyond Mars's orbit. Yet the timing of its arrival created an unprecedented scientific opportunity. The comet would make its nearest pass to Mars on October 3rd, 2025, then sweep close to Jupiter in March 2026 before disappearing into the cosmic void. Perihelion, the moment of closest approach to the Sun, would occur on October 30th, 2025, at a distance of 1.4 astronomical units, position the object perfectly for coordinated observations across multiple planets. For planetary scientists, this narrow window represented a once-in-a-lifetime chance to gather data from multiple vantage points. Every available instrument would be mobilized: the Hubble Space Telescope, the James Webb Space Telescope, Mars orbiters, and countless ground-based observatories. The urgency was undeniable. C/2025 I-3 Atlas was a singular visitor, moving too rapidly on too rare a path to ever be intercepted again. Every observation mattered because once it vanished beyond our reach, the solar system might not encounter another object like it for decades or centuries. Outgassing defines a comet's behavior. Jets of vapor and dust erupt from the sunlit surface, functioning like miniature rocket thrusters. Each burst should nudge the nucleus, producing subtle but measurable changes in its trajectory. With C/2025 I-3 Atlas, telescopes captured abundant jet activity as it approached the Sun, yet the expected recoil never materialized. Tracking teams scrutinized astrometric data from Hubble, the Very Large Telescope, and dozens of ground stations, searching for even the faintest non-gravitational acceleration. The numbers remained rock solid. Negligible deviation. Orbital solutions governed by gravity alone. This contradicts everything we know about normal cometary behavior. Even minor outbursts typically push a comet off course by meters or kilometers over time. Here, the effect was so insignificant that orbital analysts began questioning the object's mass. If the nucleus truly spanned several kilometers yet shrugged off jetting activity, like a boulder ignores a garden hose, the implied mass could reach 73 trillion pounds, a figure circulating among specialists, though not yet confirmed in mainstream journals. For context, that would make it heavier than the largest known comet in our solar system by orders of magnitude. Imagine firing a CO2 extinguisher in the vacuum of space and watching the canister float completely unmoved. That's the paradox at the core of C/2025 I-3 Atlas. Every jet should have inscribed a fingerprint on its trajectory. Instead, the comet barreled forward, utterly indifferent to its own violent activity. The mass anomaly isn't merely a curiosity. It's the first link in a chain of clues suggesting that something about this visitor fundamentally defies our expectations. Instead of the classic brilliant tail slicing across the heavens, C/2025 I3 Atlas presents an entirely different spectacle. Hubble imaging reveals a luminous, diffuse envelope, an ionized shroud that wraps the comet in a soft emerald haze. The usual sharp demarcation between coma and tail has vanished. Instead, the entire structure appears to glow uniformly, with the brightest regions stretched along a single axis. The core isn't spherical like most cometary nuclei. It appears elongated, almost cigar-shaped, a detail that stands out even in the highest resolution frames. Astronomers note that the envelope extends far beyond what's expected for a typical comet of this size. Rather than a narrow stream of dust trailing behind, the material disperses evenly in all directions, forming a halo that resists the solar wind's relentless push. The emerald hue suggests ionized gases, likely cyanogen or diatomic carbon, excited by solar radiation, but the sheer scale of the shroud remains unexplained. This morphology baffles comet scientists. Solar system comets almost invariably develop a sharp, sun-facing dust tail as they approach perihelion. Here, the envelope remains broad and diffuse, with the elongated core suspended at its center. The structure raises fundamental questions about how light scatters through this cloud, setting the stage for the next anomaly, one that challenges even our most sophisticated dust models. Light from C/2025 I3 Atlas behaves in a manner that has left comet scientists desperately searching for answers. When astronomers measure its polarization, the orientation of scattered sunlight, they discovered a record-shattering negative value, minus 2.77% at a phase angle of just 6.4 degrees. In simpler terms, this means the light emanating from the comet is polarized in the opposite direction from what's expected at that angle, and by a magnitude far exceeding any catalog comet, centaur, or trans-Neptunian object. Most comets only achieve negative polarization around minus 1.5 to minus 2%, and only at slightly larger phase angles. The polarization curve for C/2025 I3 Atlas is both deeper and narrower with the inversion point, where polarization shifts from negative to positive, occurring at 17 degrees, tighter than any known case. Teams using instruments like the VLT's FIRST 2 and the Nordic Optical Telescope's Alphos cross-verified their results, ruling out instrument error or calibration mistakes. The data held firm across 3 independent telescopes, each confirming the same extreme negative branch. Simulations using every conceivable combination of dust size, porosity, and composition failed to reproduce the observed curve. Not even the most exotic laboratory analogs, fluffy aggregates, carbon-rich grains, or icy clusters, could match both the depth and the phase angle profile simultaneously. This leaves cometary dust models at an impasse, with no known natural process capable of explaining such strong and sharply defined negative polarization. The scattering behavior of C/2025 I3 Atlas S-coma dust is, for now, an outlier in the solar system's entire catalog, a second layer of strangeness that deepens the enigma. September 2025 brought a period of intense solar activity, with space weather monitors tracking a series of coronal mass ejections. Throughout this turbulent period, astronomers maintained close surveillance on C/2025 I3 Atlas, expecting any significant solar storm to leave visible scars. Historically, powerful CMEs have torn tails off comets, triggered sudden brightness surges, or even shattered fragile nuclei. Yet as the sun unleashed torrent of plasma and magnetic fields across the inner solar system, C/2025 I3 Atlas pressed forward untouched. No sudden outbursts, no fragmentation, no dramatic changes in its luminous envelope appeared in the logs from Solar Orbiter, SOHO, or ground observatories. Solar physicists reviewing the event windows found no evidence of a direct impact or measurable disruption. The comet's coma remained remarkably stable, resisting the kind of chaos that solar storms routinely inflict. For a visitor from interstellar space, this quiet endurance is extraordinary. The absence of any tail disconnection or rapid erosion, even during peak solar weather, reinforces the earlier hints of exceptional mass and structural integrity. In the absence of the usual cometary drama, researchers face a puzzle. What kind of object shrugs off the sun's most violent outbursts without leaving a trace? The resilience of C/2025 I3 Atlas under solar assault adds yet another layer to its expanding list of mysteries. The orbital path of C/2025 I3 Atlas cuts almost parallel to the solar system's main stage. Its inclination, just 5 degrees off the ecliptic plane, places it in exceptionally rare company among known interstellar visitors. Most objects arriving from interstellar space approach at steep angles, missing the planetary plane entirely. Here, the geometry is radically different. C/2025 I3 Atlas will pass close to Mars in early October 2025, then sweep by Jupiter in March 2026, tracing a line that seems almost tailored for planetary encounters. Astronomers have attempted to calculate how probable this alignment is. Initial back-of-the-envelope calculations suggest that for a random interstellar object to cross within 5 degrees of the ecliptic, the odds fall well below 1%. That's before factoring in the additional probability of near misses with 2 major planets in a single passage. The result is a combination so rare that some dynamicists hesitate to assign a probability without running full-scale simulations. This geometry raises questions that transcend celestial mechanics. Some members of the astronomical community have cautiously floated the idea of an engineered survey trajectory, a path designed to maximize planetary flybys in one sweep. Mainstream explanations point to detection bias. Telescopes are more likely to spot objects near the ecliptic, so perhaps it's not as improbable as it appears. Still, the alignment stands out. Whether by cosmic accident or something more deliberate, C/2025 I3 Atlas is following a route that demands scrutiny, establishing new layer of mystery before discussions of chemistry or missing data can even begin. Spectrographs aimed at C/2025 I3 Atlas have detected a volatile cocktail that doesn't conform to the usual script. The coma glows with emissions from cyanogen and carbon monoxide, 2 gases common in comets from the outer reaches of our solar system. But the proportions here are anomalous. The CN to CO ratio, debated in late-night calibration sessions from ALMA to Mars Express, lands much closer to what scientists observe high above Mars than in any Oort cloud or Kuiper Belt visitor. That's surprising. Solar system comets typically show water dominance with much lower concentrations of these volatiles, especially at such distances from the Sun. Here, the CN and CO spectral lines stand out prominently, sometimes even outshining water signatures, depending on the instrument and observation timing. The Mars analogy keeps resurfacing. Some ESA teams have noted that the volatile inventory in C/2025 I3 Atlas S-coma could almost be mistaken for a snapshot of the Martian upper atmosphere, rich in carbon compounds with chemistry suggesting formation in a cold, carbon-heavy environment. Yet not everyone is convinced. Instrument specialists caution that at these distances, signal-to-noise ratios are challenging and background subtraction can shift the ratios in either direction. Still, the chemistry is difficult to dismiss. If these measurements hold up under further scrutiny, they raise a profound question. Did C/2025 I3 Atlas form in a planetary environment? Or is it carrying the chemical fingerprint of a world long lost to interstellar space? The answer could heavily influence which hypothesis, natural formation, planetary seeding, or engineered origin, gains credibility as more data arrives. During the final approach to Mars, an unusual silence descended over official data streams. For 11 days in 2025, NASA's public feeds tracking C/2025 I3 Atlas went dark. No updates appeared in the Near-Earth Object Program's logs, and the Deep Space Network's routine status bulletins offered no explanation. The timing raised eyebrows. This blackout coincided precisely with the comet's most favorable viewing geometry from Mars and a critical window for cross-mission imaging. Requests for internal emails and tracking logs under the Freedom of Information Act have yielded little so far, just generic shutdown notices and maintenance schedules with no direct reference to a deliberate data embargo. The information vacuum fueled speculation. In late September, a claim surfaced online, a faint streak in a Perseverance rover navigation camera image, supposedly captured during the blackout, might be C/2025 I3 Atlas. The image, debated in forums and amateur circles, remains unverified by JPL or NASA archives. No official statement has confirmed or denied its authenticity, and raw data files show no flagged anomalies. Meanwhile, rumors persist that classified radar observations, possibly from U.S. Space Force assets, exist but remain withheld from public release. No such records have surfaced, and institutional responses have been uniformly noncommittal. For comet researchers, these gaps represent more than curiosity. They highlight the tension between open science and institutional caution. When rare, high-profile objects sweep through the solar system, without transparent data sharing, the boundary between technical delay and intentional silence blurs, leaving both the scientific community and the public searching for answers in the shadows. Three rival interpretations now compete to explain C/2025 I3 Atlas. The first casts it as a rare but natural comet, shaped by the unpredictable violence of planetary system evolution. Supporters argue that our sample of interstellar objects is minuscule, and new arrivals may simply reveal chemistries or structures we haven't encountered before. Karen Meach, a leader in interstellar comet research, urges restraint, reminding colleagues that all known cometary behaviors are subject to observational bias and sample limitations. Extraordinary claims, she emphasizes, must be matched by extraordinary, quantifiable evidence. A second, less conventional hypothesis suggests C/2025 I3 Atlas is a planetary seed, a fragment ejected from a young stellar system, carrying the raw materials for planet formation. The object's unusual chemistry and mass fuel this speculation, hinting at a deeper role in cosmic evolution beyond simple comet activity. The most provocative theory comes from Avi Loeb, who argues that the object's mass, polarization measurements, and trajectory elevate the probability of artificial origin to 30 or 40%. For Loeb, the absence of a convincing natural explanation is itself evidence, though he concedes that without direct physical evidence, the claim remains unproven and speculative, with the clock ticking on C/2025 I3 Atlas. S departure, the next phase focuses entirely on measurement. Teams have mapped out a comprehensive observational checklist. After perihelion on October 30th, 2025, Earth-based telescopes regained their optimal viewing window by December. The Hubble Space Telescope and James Webb Space Telescope are both scheduled for follow-up imaging and spectroscopy, targeting the comet's nucleus and coma for any late-stage surprises. The Atacama Large Millimeter Array will track gas ratios with unprecedented precision, aiming to definitively resolve the CN and CO chemistry that has generated so much debate. Meanwhile, ESA's Mars Express and ExoMars Trace Gas Orbiter are positioned to collect data as the comet departs Mars's vicinity, offering a rare cross-check from another planetary perspective. The real wild card arrives in March 2026 when C/2025 I3 Atlas approaches Jupiter. Ground-based observatories and potentially ESA's JUICE mission can monitor for any changes in trajectory or outgassing patterns triggered by Jupiter's immense gravitational field. Each observation functions as a test. Does the mass anomaly persist? Does the polarization curve remain consistent? Does the chemical signature hold steady? The answers will emerge not from speculation, but from this coordinated campaign of eyes on the sky. The scientific method is clear. What happens next will be decided by the data alone. Every anomaly in C/2025 I3 Atlas pushes the boundaries of what comet science can explain. If even a handful withstand rigorous scrutiny, the textbooks on interstellar objects will require fundamental rewriting. The stakes extend far beyond academic curiosity. Each unexplained property, mass, polarization, trajectory, chemistry, forces scientists to revisit basic assumptions about how matter travels between stars, how planetary systems form and exchange material, and how rare or common engineered artifacts might be across a galaxy. The next wave of data could determine whether C/2025 I3 Atlas becomes a case study in natural extremes or the first credible indication of something built rather than born. This is why the world's most powerful telescopes remain locked on target. This is why open access to every measurement matters. The outcome will shape how astronomers search for technosignatures, how space agencies prioritize rapid response missions, and how humanity engages with the search for life and intelligence beyond Earth. With each new observation, the central question deepens. What exactly just passed through our solar system? What's unmistakable is that C/2025 I3 Atlas challenges established comet science at every turn. Its continued observation by ALMA, Hubble, and JWST may soon determine whether these anomalies point to natural extremes at the edge of possibility, or something unprecedented in human experience. For now, the evidence leaves the door wide open. The universe has presented us with mystery, and the answer lies waiting in the data yet to come. As C/2025 I3 Atlas races toward its closest approach to the Sun, astronomers have identified several critical measurements that could either resolve the mystery or deepen it beyond recognition. The polarization anomaly alone could rewrite our understanding of dust grain formation in interstellar space. If follow-up observations confirm the extreme negative values persist at different phase angles, it would force physicists to develop entirely new scattering models, or accept that the material comprising this object differs fundamentally from anything we've studied. The mass calculation presents an even more dramatic challenge. Standard density estimates for cometary nuclei hover around 0.6 grams per cubic centimeter, essentially dirty snowballs held together by gravity and volatile ices. But if C/2025 I3 Atlas truly masses 73 trillion pounds while maintaining its observed size, the implied density would approach 2 to 3 grams per cubic centimeter. That's closer to solid rock or metal than ice. For an object actively outgassing like a comet, this combination seems physically impossible under conventional models. Teams at the European Southern Observatory are preparing a detailed spectroscopic campaign to measure the nucleus's rotation period with precision. If the elongated core is tumbling chaotically rather than rotating smoothly, it would suggest a violent ejection from its parent system, perhaps a catastrophic collision or close encounter that sent fragments screaming into the void. But if the rotation is stable and predictable, it raises uncomfortable questions about structural integrity that natural formation processes struggle to explain. The October 3rd, 2025 flyby of Mars represents more than just a close encounter. It's a natural experiment that could reveal the object's true nature. Mars possesses a thin but measurable atmosphere, and any interaction between the comet's coma and Martian atmospheric gases will be detectable by the suite of orbiters stationed around the red planet. The MAVEN spacecraft, designed specifically to study Mars's upper atmosphere, can measure any disturbances or chemical exchanges as C/2025 I3 Atlas sweeps past. If the comet's volatile inventory truly mirrors Martian atmospheric composition, this flyby might trigger detectable resonances, chemical signatures that would either support the planetary fragment hypothesis or demolish it entirely. More intriguingly, the Mars Reconnaissance Orbiter's high-resolution cameras could capture the nucleus in unprecedented detail at distances far closer than any Earth-based telescope can achieve. These images might resolve surface features, reveal active venting regions, or detect structures that don't match natural erosion patterns. The data from this encounter alone could tip the scales between natural and artificial origin theories. But there's another possibility that mission planners are quietly discussing. What if C/2025 I3 Atlas alters its trajectory during the Mars flyby? Any deviation from the predicted path that can't be explained by Mars's gravity would be profound. It would suggest either an internal mass distribution far more complex than assumed or active maneuvering capability. Either explanation would be revolutionary. While Mars offers a first close-up opportunity, Jupiter presents the ultimate test. When C/2025 I3 Atlas sweeps past the gas giant in March 2026, it will enter the most powerful gravitational field in the solar system outside the Sun itself. Jupiter's gravity has torn comets apart, captured asteroids into permanent orbits, and sculpted the architecture of the entire outer solar system. What Jupiter does to C/2025 I3 Atlas, or more importantly, what it doesn't do, could be the most revealing data point of all. If the comet passes through Jupiter's influence without any measurable perturbation beyond what Newtonian mechanics predicts, it will confirm the extraordinary mass estimates. But it would also eliminate virtually every natural formation scenario currently on the table. There's a darker possibility that few scientists are willing to discuss openly. What if C/2025 I3 Atlas doesn't follow a purely ballistic trajectory past Jupiter? What if it adjusts its path, however slightly, in response to Jupiter's gravity well? Such behavior would be inconsistent with a passive object governed solely by natural forces. Ground-based radar facilities are preparing to ping C/2025 I3 Atlas with radio waves during the Jupiter encounter. The return signal would reveal the surface composition, detect any metallic components, and potentially identify geometric structures hidden beneath the glowing coma. These radar observations, if successful, could provide the smoking gun evidence that settles a debate or ignites an entirely new one. The 11-day data blackout surrounding the Mars approach hasn't gone unnoticed by the scientific community. While official explanations cite routine maintenance and data processing delays, the timing remains suspicious. In an era of real-time data streaming and automated observation protocols, an 11-day gap in coverage during the most scientifically valuable observation window demands explanation. Freedom of Information Act requests filed by independent researchers and science journalists have so far been met with bureaucratic delays. Preliminary responses acknowledge that certain observational data exists, but cite national security exemptions and ongoing analysis as reasons for withholding public release. This pattern is familiar to those who followed the initial Oumuamua controversy, where speculation outpaced official disclosure for months. The alleged Perseverance rover image showing a streak across the Martian sky has become a focal point for amateur investigators. Frame-by-frame analysis of publicly available rover navigation camera data has revealed several unexplained light sources and transient objects, though none definitively match the predicted position and brightness of C/2025 I3 Atlas. JPL's silence on the matter, neither confirming nor denying the existence of such images, only deepens a mystery. More troubling are reports from amateur astronomers who claim their telescope time requests to observe C/2025 I3 Atlas during the Mars encounter were denied or redirected without explanation. Several university observatories reported unusual interference in their scheduled observation windows, with some experiencing unexplained equipment malfunctions during critical periods. While most of these incidents likely have mundane explanations, the pattern is difficult to ignore. Avi Loeb's assessment that C/2025 I3 Atlas has a 30 to 40% probability of artificial origin isn't made lightly. Loeb, director of Harvard's Galileo Project, has staked his reputation on the search for extraterrestrial artifacts in our solar system. His analysis considers several factors that, when combined, paint a disturbing picture. First, the trajectory. The probability of a random interstellar object arriving on a low-inclination path that facilitates close encounters with two major planets is vanishingly small. Loeb argues that deliberate targeting would explain this geometry far more elegantly than cosmic coincidence. Second, the mass-to-outgassing ratio defies known comet physics. An object that jets material, yet shows no momentum transfer, behaves more like a controlled propulsion system than passive sublimation. Third, and perhaps most compelling, is the polarization signature. Loeb's team has modeled various artificial materials, metals, ceramics, synthetic polymers, and found that certain engineered surfaces could produce exactly the kind of extreme negative polarization observed. Natural materials, by contrast, consistently fail to match the measurements. Critics counter that absence of natural explanation isn't evidence of artificial origin. Karen Meach points out that our sample size of interstellar objects remains statistically insignificant. We confirmed only 3, 1I/Oumuamua, 2I/Borisov, and now C/2025 I3 Atlas. Drawing conclusions from such limited data is premature. Each new discovery expands our understanding of what's possible in nature, rather than confirming what's artificial. But Loeb poses a challenging question. At what point does wait for more data become an excuse for avoiding uncomfortable conclusions? If C/2025 I3 Atlas exhibits 5, 6, or all 7 anomalies that defy natural explanation, how many confirmed cases do we need before considering alternative hypotheses seriously? If, and it remains a significant if, C/2025 I3 Atlas proves to be an engineered object, the implications cascade across multiple fields. The most obvious question is intent. Is this a probe deliberately surveying our solar system's planetary composition? The trajectory certainly suggests systematic observation, a low inclination path that maximizes planetary encounters while maintaining safe distances. The chemistry becomes more intriguing under this hypothesis. If the volatile inventory mimics Martian atmospheric composition, perhaps it's not coincidence but camouflage, a way to blend with natural objects while conducting close-range observations. The extreme mass would make sense as radiation shielding or structural support for sensitive instrumentation. The lack of trajectory change from outgassing could indicate controlled venting, using jets not for propulsion but for thermal management or course correction. So precise, it appears gravitationally bound. The timeline is equally fascinating. C/2025I3 Atlas has been traveling through interstellar space for potentially millions of years before entering our solar system. If artificial, it represents technology deployed on timescales that dwarf human civilization. Whatever launched it either possessed extraordinary patience or no longer exists to receive its data. Some researchers have explored even more speculative scenarios. Could C/2025I3 Atlas be a von Neumann probe, a self-replicating explorer that manufactures copies of itself from raw materials? The planetary seed hypothesis takes on new meaning under this interpretation. Perhaps what appears to be unusual chemistry is actually a manufacturing signature, the remnants of material processing for self-replication. Before embracing exotic explanations, we must exhaust natural possibilities. Several astrophysicists have proposed scenarios that could explain at least some of C/2025I3 Atlas. S anomalies without invoking artificial origin. The mass anomaly might result from unusual internal structure. If the nucleus contains a dense metallic core, perhaps iron or nickel from a shattered protoplanet, surrounded by a volatile ice shell, it could produce the observed combination of high mass and active outgassing. The momentum transfer from jets might be masked by the overwhelming inertia of the metallic core. The polarization measurements could reflect an exotic dust composition we haven't synthesized in laboratories. Interstellar space contains complex organic molecules, carbon chains, and even amino acids. Dust grains coated with layered organic tars might scatter light in unexpected ways, producing extreme negative polarization through interference effects we haven't modeled yet. The trajectory, while statistically improbable, isn't impossible. Detection bias strongly favors finding objects near the ecliptic plane. We're most likely to spot what passes through our telescope's primary search zones. Billions of interstellar objects might traverse the solar system at steep angles, completely missed by our surveys. The few we detect naturally cluster near the ecliptic, not because they're aimed there, but because that's where we're looking. The chemistry could reflect formation in an unusual stellar environment. Some young star systems are carbon-rich rather than oxygen-rich, potentially producing comets with compositions unlike anything from our Oort cloud. The Mars similarity might be coincidence. Both environments involving cold, carbon-dominated chemistry in planetary contexts. As Earth's viewing geometry improves in December 2025, the astronomy community has organized an unprecedented coordinated observation campaign. Over 50 institutions across 6 continents will simultaneously target C/2025I3 Atlas using every available technique: optical spectroscopy, radio imaging, infrared analysis, and polarimetry. The December campaign has specific objectives designed to test each anomaly. Hubble will attempt to resolve the nucleus at maximum magnification, searching for any geometric regularities that might indicate artificial structure. JWST will perform deep infrared spectroscopy, mapping the coma's chemical composition in unprecedented detail and searching for molecular signatures that don't match any known natural process. Ground-based facilities will conduct intensive polarization measurements across multiple wavelengths and phase angles. If the extreme negative polarization persists under varying conditions, it would eliminate several natural explanations and narrow the possibilities considerably. Conversely, if the polarization normalizes as the comet's geometry changes, it might reveal a transient effect caused by temporary dust alignment or viewing angle. ALMA will dedicate observation time to mapping the gas distribution around the nucleus at millimeter wavelengths. These measurements can distinguish between passive sublimation and active jetting, potentially identifying vending patterns that suggest internal structure or, more provocatively, controlled emission. C/2025I3 Atlas has captured public imagination in ways that previous interstellar visitors didn't. Oumuamua sparked brief interest, but faded from mainstream attention before definitive answers emerged. 2I/Borisov, despite being more thoroughly studied, was too conventionally comet-like to sustain widespread fascination. C/2025I3 Atlas is different. The combination of multiple unexplained anomalies, suggestive timing of data blackouts, and serious scientific figures discussing artificial origin has created a perfect storm of public interest. Social media platforms have exploded with amateur analysis, computer-generated visualizations, and heated debates about the implications. This public engagement brings both benefits and risks. On one hand, distributed amateur astronomers have contributed valuable observations, catching transient events and providing continuous coverage that professional facilities can't match. Citizen scientists have processed terabytes of archival data, identifying potential earlier detections and refining trajectory models. On the other hand, speculation has occasionally outpaced evidence. Conspiracy theories have emerged suggesting government cover-ups, secret contact attempts, or even claims that C/2025I3 Atlas has already communicated with Earth authorities. These narratives, while entertaining, muddy the scientific discourse and make it harder for the public to distinguish legitimate mysteries from pure fantasy. Scientists face a delicate balance, maintaining transparency while avoiding premature conclusions. Every preliminary result released to satisfy public curiosity risks being misinterpreted or sensationalized. Yet withholding information only fuels suspicion and undermines trust in the scientific process. The C/2025I3 Atlas case may become a template for how astronomy handles future high-profile discoveries in the age of instant global communication. The countdown continues. The telescopes remain locked on target. And somewhere in the darkness between stars, C/2025I3 Atlas keeps its secrets, waiting to see if we're clever enough to unravel them before time runs out. On a clear night in August 2026, Dr. Sarachin stood outside the observatory where it had all begun, looking up at the stars. C/2025I3 Atlas was out there somewhere, invisible now, racing toward its next destination at speeds no human craft could match. "Do you think they know?" her colleague asked, standing beside her. "The ones who built it. Do you think they know it reached us?" Chin smiled slightly. "Maybe, or maybe they're gone, and that probe is all that's left of them. An entire civilization reduced to a single machine, still carrying out its mission long after creators turned to dust." "That's a lonely thought." "Or inspiring," Chin countered. "Think about it. Even if they're extinct, they still reached us. They still touched our world, changed our understanding of the universe, made us feel less alone. Their probe outlived them. Their legacy continues. That's not defeat. That's immortality. Above them, the stars shone in their billions. And somewhere among them, 1,200 light-years away, 47 light-years in another direction, and in countless unknown locations across the galaxy, other probes were traveling. Other voyagers were journeying, carrying other stories from other worlds. The question wasn't whether we were alone. C/2025I3 Atlas had answered that definitively. The question was, what would we do with the knowledge? How would humanity respond to the revelation that the galaxy was filled with explorers, that the universe itself was crisscrossed with ancient messengers carrying word from civilization to civilization across time and space? Dr. Chin looked at the sky and thought about the probe humanity would eventually send, the one that would carry our message, our story, our answer to the question that C/2025I3 Atlas had posed simply by existing. The conversation had begun, and it would echo across the stars for as long as stars continue to burn. 1 year after the Jupiter encounter, an amateur astronomer in Australia detected a faint radio signal during a routine scan of the Eridanus constellation. The signal was weak, distant, but its pattern was unmistakable. Prime numbers, followed by mathematical constants, followed by star maps. It wasn't C/2025I3 Atlas. That probe was still years away from its destination. traveling in silence. This was something else. Another probe, another explorer, another message from another civilization, crossing our skies in the endless dance of galactic exploration. The detection was confirmed within hours. Trajectory analysis began immediately. This new visitor would make its closest approach to the solar system in 14 months, passing within observation range of our telescopes. And this time, humanity was ready. The rapid response mission launched 3 months later, a spacecraft racing to intercept the visitor, to observe it up close, to perhaps, finally, answer the questions that C/2025I3 Atlas had left tantalizingly unresolved. The age of discovery had begun. The galaxy was speaking, and humanity, at last, was learning to listen. The story of C/2025I3 Atlas wasn't an ending. It was a beginning, and the greatest mystery still lay ahead, waiting among the stars.